In the EU, aging societies and chronic infirmities are unstoppable phenomena, resulting in a loss of autonomy and a breakdown of social bonds. Innovative assistive technologies, such as social assistive robotics and smart-powered wheelchairs, play a critical role in empowering disabled and elderly persons while also improving social inclusion. There are many roadblocks to the adoption of assistive technologies: standardization, interoperability, limited involvement of users, lack of healthcare professional trainings. Through our project, we aim to address some of these challenges. Our main focus was on two main components. The first was to develop a simulation platform to provide an immersive experience for users of driving a smart-powered wheelchair. This would allow training of users to drive a wheelchair in everyday life while also allowing professionals to assess the wheelchair's applicability for certain patients and surroundings, as well as get a user's perspective. The second focus was to develop a smart-powered chair to compensate for user impairments with driving assistance technology while also providing health reports, which would allow healthcare providers to track changes in a user's health more easily. This can benefit severely disabled users by increasing their level of autonomy and improving quality of life. Through a literature review and through our partners' clinical studies, we've identified key demographics which make for good candidates that could benefit from the types of assistive technologies that we focus on. We would now like to take you through some of the things that our robotics team at University of Kent has been developing. Our smart wheelchairs have collision avoidance capabilities as well as the ability to be controlled remotely through a smartphone application. With the help of sensors placed around the wheelchair, our algorithms are able to detect and avoid obstacles, prevent accidents and offer the user more flexibility and freedom, and reduced mental load. The system is tolerant to noisy inputs such as spasms or rapid hand jerks, while still able to safely move through difficult environments. In this demonstration, our researcher only needs to direct the wheelchair forward, and correcting the direction is handled for him. The anti-collision system allows for easy negotiation of the obstacles in the environment with minimal input from the user. This is implemented using inexpensive off-the-shelf sensors, such as ultrasound, infrared and time-of-flight sensors that provide information about the wheelchair's surroundings. We've also developed smartphone applications which give visual and auditory feedback to the user, similar to a car's parking sensors. We've also used AI techniques to teach a simulated wheelchair to navigate a course with ramps and narrowing corridors. Using artificial intelligence techniques, we perform head tracking in real time. With the head tracking solution, an individual can control the wheelchair by simply moving their head in the direction they wish to travel. This can enable a quadriplegic individual to be able to control a wheelchair without the use of their limbs. The system consists of a low-cost webcam facing the user and a small form-factor computer which runs the AI algorithms. This is a less invasive and much more intuitive means of driving a powered chair, when compared to sip and puff or chin-controlled joysticks. In our experiments, we've had users perform figure eights with a narrow angle, navigating a narrow corridor and stopping at a specified point. All of the computations are done in real time on the integrated system on board of the wheelchair, while also recording the trial data. Another focus was in identifying objects within the environment to provide feedback to visually impaired users who may suffer from semi-neglect or short-sightedness. The system we developed allows objects to be recognized and displayed on a convenient interface to the user. The video demonstrates how the system classifies different categories of objects and presents each category under a specific color. The system also tracks objects of interest and presents them to the user. Distance from that particular object is provided on their display, so that they can assess their environment and plan accordingly. To provide health monitoring, we employ the use of smart wearables. These provide a means to monitor the user's physiological metrics such as heart rate and blood pressure, for health monitoring, and to ensure and improve on their comfort level. For posture monitoring, we have developed a smart cushion which allows posture monitoring and adjustment. This can reduce the formation of pressure sores by inflating or deflating individual cells, to compensate for differences in pressure and redistribute it evenly. Here you can see one of our researchers using the HTC Vive VI headset with one of our smart wheelchairs on the actuated platform developed in our lab. The purpose of our research is to develop a hardware-software platform to enable wheelchair users to practice navigation within a safe and bespoke virtual environment. The platform allows the users to learn new complex skills that would otherwise be challenging to learn in real life. The platform provides an interface for clinicians to set the required training and to collect/analyze data from the users. Wearable sensors are used to collect users' physiological measurements such as heartbeat and eye movement during the training. Through a literature review, we have identified many benefits which VR can offer, such as training in a safe environment and transfer of acquired skills to the real world. Nonetheless, to make the system viable, some limitations need to be overcome, such as cybersickness. The hardware-software platform we developed, which is based on VR, enables wheelchair users to practice navigation and is characterized by two modalities. The first one is placed in a clinical setting and in conjunction with a mechanical simulator. The user sits on their wheelchair, placed on top of the mechanical simulator, which mimics the experience of traversing real terrains and providing the user with more realistic sensory feedback of the experience. In the second modality, the system is used in the user's home. This allows the training to be conducted using a VR headset and a joystick mimicking the joystick on the user's wheelchair. This allows the user to train whenever possible, whilst allowing the clinician to track the user's progress remotely. In both modalities, the virtual environment contains game-like features, such as point score systems and tracking of the user's movement, in order to provide an engaging and motivating experience. Data, such as performance-related parameters such as reaction time, completion time, deviation from set path and the patient's physiological measurements, are collected during the training. Physiological measurements are taken in order to monitor the trainee's well-being throughout the training. Online questionnaires are conducted to know how the user felt during the training. Furthermore, throughout the development stage, meetings with clinicians, who work closely with wheelchair users, have been undertaken to make sure the platform meets the required needs. From our point of view, the main technical challenges throughout this project can be classified in three categories. The biggest challenge from a technical perspective represents the integration of a diverse range of components within a complex system, and the evaluation of these technologies. The second challenge was that of communication between interdisciplinary branches such as healthcare professionals, engineers, businesses and administrators, and the third was that of training of individuals to help each understand different aspects of an interdisciplinary framework. Thank you for your attention.